bonus technique, the grapefruit.
Sorry, was someone in the middle of asking a question? Okay, so let's start. We're still waiting for people, but time is short. So okay, so let's again start with trying to get Zoom to move the slides. Okay, so again, I'm getting a lot of questions about the websites, and that's an indication to me that many of you don't know that we have a website and don't know that all the information is on the website. So not only the lectures are there, the homework is there, the solutions are there, the quizzes are there. So basically go to the website, explore it a little bit more if you haven't done so in the first half of the class. And in particular, please look at the lecture notes and the slides and try to do this even before class. I think that's going to help all of us. Okay, so I assume you all know this. Homework 2 has passed. Late submissions, maximally late submissions are due today. And the solutions for homework 2 are also going to be available today. Quizzes. I'm not going to show the quiz 6 statistics. I just want to say that I thought everyone did very well. One comment on this, I noticed that, so the average grade is about 95%, and almost all of you did the quiz. It's a good suggestion to go over quizzes because the type of questions that you'll see in the exams is similar. I just noticed that the one problem that causes some of you problems in the quiz was the first problem that had to do with counting. One advice on this is try some cases. So don't just think about it generally, but try to take dimension 2 or dimension 3, write it down, and verify that your thinking is correct. Okay, so let's talk a little bit about the exam. I'm sure this is a question on your mind, at least those that are already here. Okay, midterm is going to be quiz style. It will be done on Canvas. We're going to open Canvas at 10:30 on Wednesday and close it an hour later. We're still thinking whether it's going to be 60 minutes or 80 minutes. If people have a strong view on that, you can let me know. But that's the way it's going to be, except for people that have been approved for extended time. All of you, some of you I've been in touch with, some of you, all of you will get an email from me sometime today. You need to be on Zoom, and I'd appreciate if all of you open your videos, if at all possible, so that you can communicate with us easily. The questions are going to be short questions, multiple choice. A few will require filling in answers, but most will be multiple choice. There are going to be quite a few questions. So as I said, it's quiz style, so these are short questions, open books, so you can prepare any material that you want if you need to consult something, but I don't think you're going to have a lot of time to consult it. So because there's going to be quite a few questions, but we're going to try to make it about understanding rather than memorization. So you don't need to memorize too many things. You need to understand what's happening. In a couple of cases where we think that you need to know some formulas, we're going to supply these formulas in the exam itself. Again, you may not need it at all, but it will be there. Questions? That's the best time to ask questions about it, because I'm going to move on. No questions. Excellent. Okay, projects. This has been a long time coming. CIS 519 student, which is most of you, need to do a team project. Teams are going to be size 2 to 4. I realize that the current situation isn't the best situation for to facilitate grouping. We're going to help with that if needed. The key change from previous years is that we're going to have just probably 3 projects or a little bit over 3 projects, so it's not going to be completely open. We are going to provide initial ideas and data sets. You will, in your team, will have to think about it, write a short proposal or a plan of what you're going to do with what we suggest, and then you're going to work on it in the next months and a half or so. If you have an idea for a project and you would like this to be one of the project teams are working on, put it in writing quickly before the end of this week. If you have a data set or a problem that you think is interesting and has data, write it down, a short description, motivation, the data that is available, any other relevant information, and send it to me before the end of this week. We're going to supply more details on the website, but you can start teaming up. Now, the project is going to be, of course, a machine learning project. You'll have to develop a small machine learning system and run experiments with it, but it's not going to be only, I'm comparing a few algorithms on this data that you gave us, but you will have to ask a question or propose some hypotheses and investigate it in the course of your project. For example, maybe the data is some medical data and you know something of the population. Maybe you want to try to separate by gender and see if you can learn from only female and make conclusion also on male. Or maybe you can divide it by age groups. Can you learn from one age group and make conclusion also on other, and so on. So you can come up with any hypothesis that makes sense to you and try to investigate it with the data. Questions on this? Okay, I see so far that a few people commented on the chat about the time for the exam. One important thing to note is that everyone is going to have the same time. So whether it's 60 minutes or 80 minutes, it's the same for all of you. We're going to open it at one point in time, close it in another. So and we realize, in fact, I design it in such a way, hopefully it's going to work, that you will not finish all the questions we ask you. And the reason is that I think that exams that are too easy are unfair to the students, because basically differences between students that eventually translate to grades are becoming accidental. If the exam is harder, then if you know something, it will show the differences are going to be spread out. So that's what we're going to try to do. I don't know if we succeed or not, but so don't worry about whether it's 60 or 80. It's going to be the same for all of you, and hopefully it will allow you to figure out how good you know the material and allow us to know something about this also. Okay, no questions, so let's move on. Okay. Okay, so let's see where we are in class. So we talked about algorithms, we talked about several learning models, and the next, today and next time, we're going to talk about generalization. Really, the key questions in machine learning is, when does it work? Why does it work? And I want to spend a little bit of time this semester to basically address these kind of questions. So what we're going to do in the next 2 meetings is really develop a theory of generalization and show what does it mean to develop a theory of generalization, and what kind of things we can say about learning algorithms, about learnability in general, and so on. This has several I mean, there are several reasons why we want to do this beyond just understanding the theoretical underpinning of learning. It turns out that there are also some really important insight that we can gain from understanding the theory. And after the chapter on theory, we're going to spend a little bit of time figure out what are the algorithmic implications, or what are some algorithmic implications of understanding the theory. Okay, so first of all, the key question that we are addressing is, why does learning work? And the basic theorem we're going to discuss is going to have the following form. On the left side is going to be the error of the model that we learn, which is the true error on a sample from the distribution. And we're going to show that this one is bounded by the training error plus some complexity term. And the key question is, what is this complexity term? So what is the gap between the training error and the true error that we're going to see in the real world? So, of course, in order to show something like this, there's going to be some conditions. And the key condition is going to be that the training data is sampled from the same distribution as the test data. We're going to give it a name. It's going to be called IID, independently identically distributed. And as I said, the key question is, how do we estimate this complexity term, which is the gap between what we see on training and what we're going to see in the real world? Now, of course, experimentally, you already lived through this in both homeworks that you've done. In both cases, you've experimented with several learning algorithms, and you saw that as a function of something, there are small gaps between performance on training and test, or large gaps. Recall homework 1, where you experimented with decision trees, decision stumps, and other algorithms, and you saw that they behave differently with respect to what you see on training and what you see on test. In homework 2, you've seen similar things. And for example, if you think about the second part of homework 2, where you did adaptation, you've also seen that things that you see on the training sets and similar distributions do not necessarily adapt to what you see when you try on a different data set, even if it's the same problem, the same task. So you already know something about these things experimentally, but our goal is going to be to quantify it. So an example of a result that we're going to show is something like this. We're going to show that for every distribution generating training and test instances with high probability, we're going to say at least 1 minus delta, where delta is going to be some small tolerance parameter. Let's say you're willing to suffer 5%. So with 95% probability, for all the hypotheses that we have in our hypothesis class, the true error, error D, is going to be bounded by the training error plus this constant, this term here. And when you look at this term, hopefully you understand that this makes sense, right? So this generalization term is a function of the size of the hypothesis space. So if we have a large hypothesis space, the gap is large. Think decision trees. If we have a small hypothesis space, think decision stumps. This gap between what you see on training and in the real world is going to be smaller. This gap also depends on how many examples you see, right? If you see a lot of examples, the gap is small. So the estimation that you get by looking at the error in training is going to be pretty good. If you don't train on a lot of examples, then this estimation is not going to be so good. And of course, it's going to be also a function of your tolerance parameter. Do you want to be very, very sure? You want this with very high probability, which means delta is small, or you're willing to allow larger delta? So that's the type of things we're going to show. And we want to start now. Questions on this? Okay. So in general, what we are doing here is we are giving you a window into an area in machine learning that is called computational learning theory, really trying to study the general laws that constrain or guide inductive learning. We want a theory that relates the probability of successful learning with the number of examples that we see in training, with the complexity of the hypothesis space, with the accuracy within which we want to approximate the target function, and potentially also with the manner in which training examples are presented, although we are not going to attend to this last bullet so much. But we definitely are going to talk about all these other 4 issues here. Okay, so let's start by recalling what we've already done. We talked a few weeks ago about quantifying performance, and we did it via learning conjunctions, right? So we had this target conjunction, hidden conjunction, and we asked how many examples are needed to learn it. And we talked about 3 learning protocols. We talked about the teaching protocol. We talked about an active learning protocol. This was 1. 2 was teaching, and 3 was the standard protocol. It's standard because really it's the easiest to analyze, where some random source provides training examples, nature also provides labels, and we're trying to learn a function. And that's the protocol that we're going to attend to today, this protocol which I call the 3rd protocol. And basically, if you remember, again, I'm putting here the hidden function on the top right. And this was the hidden function in the sense that when we generated examples, they were labeled according to this function. And we tried to look at this example and learn. And the final hypothesis that we got is this one, which, as you can see, is a little bit different than the hidden function. But that's what our learner managed to get. This final hypothesis was consistent with all the data we've seen. And we can see that it's a little bit different than the target one. So we asked a few questions, whether it's good, what's going to be the performance of this, and also how many examples are needed in order to actually learn this. So we also answered, at least hand-wavingly, some of these questions. We said that given the data we got, we only managed to learn some approximation of the true concept. We also said that we don't know how many examples we need to see, but we knew how many mistakes we're going to make. And that led us to two research direction, or two teaching direction potentially. One is to look at mistake-driven algorithm, where we can actually quantify how many mistakes we're going to make before we converge to an algorithm, which was very nice, very simple conceptually, and very useful, but still maybe unsatisfactory because we don't know when we're going to make these mistakes. And really, in many situations in learning, you want to know, you have to have a more robust notion of how well will I do in the future. So I learned so far, now I'm taking my hypothesis and I'm going to use it. Is it going to be good? How good is it going to be? And so on. So, and that leads to the second direction that we want to attend, which we're going to discuss today. So, and this is the probabilistic intuition that is driven by this example here. Again, reminding you, this was the true concept, a conjunction of x2, x3, x4, x5, x100. And we actually learned x1 and the rest. So we did not eliminate x1, it's still part of our hypothesis. So the probabilistic intuition that we discussed is, well, why didn't we eliminate x1? We didn't eliminate it because we never saw x1 as taking the value 0 in a positive example. Maybe we'll never see it. Maybe the distribution is so that it never happens. And if it's not, still it's probably with a small probability that this happens, because in all our training examples, we've never seen it. So maybe we don't care. So even though we kept x1 in the hypothesis, it's never going to bother us. And this is exactly the intuition that is going to underlie what we're going to call the PEC framework. PEC stands for probably approximately correct, that we're going to start discussing today. Okay, questions so far? Okay, just to remind ourselves a little bit of the notation, we're talking about an instance space X, a concept space C. It's going to be easy for us now to assume that there is a set of possible target functions that we're after. We're going to denote this space by C. And there is a hypothesis space, which is the set of all functions that our algorithm considers. We're getting a sample of training instances that I'm denoting S. And my goal is to determine a hypothesis, H in H, such that H of X is equal to the target, F of X. But I'm missing some quantifiers here. Quantifiers on X. What do I want X to vary on? Do I want X to vary on S, the training data? Or do I want X to vary on all the instance space? Hopefully, you all agree that you care about, we don't care about X varies in S, because that's easy. That's just the training data. We care about X in X on instances that we haven't seen yet and may never see in training. So really that's what we care about, to determine a hypothesis that either is equal to F or at least estimates F, but we care about evaluating it by its performance on future, previously unseen instances in X that are drawn according to some distribution. And this is where this X1 comes in. So here is the situation that we can think about. So I'm drawing this Venn diagram here, where F, the true function, is in blue, and the hypothesis that we learn is in red. The way you want to understand it is inside the circle are all the positive examples of the function. So the function, the circle defines the function, and outside the circle are all the negative examples of the function. And this big rectangle here is the universe that we have, right? If you think about Boolean examples, this is 0, 1 to the n outside, okay? So here is the situation and the intuition that we want to develop, right? So we have seen a lot of examples drawn according to some distribution that we don't know, D. Since in all the examples, X1 was active, all the positive example, X1 was active, it's very likely that it will be active in future positive examples too. If not, in any case, X1 is active only in a small percentage of the examples, as you can tell by not observing it in training. And therefore our error is going to be small. And the error is going to be measured as the probability over all x's in this distribution that f of x is different than h of x. And this is what I show here in this Venn diagram. So this is f, these are all the positive examples. I learn h, the red circle here. And what you can see here is these moon shapes are the regions where f is different than H, right? So these are positive examples of F that are outside H, so they're negative example for H. And in this region, you can see positive example of H that are outside F, so they're negative for F. And these two regions define the disagreement between F and H. Okay, so of course, the question is, can we bound this error, right? That's the goal of learning, right? So we want to be able to bound the disagreement between F and H so that we'll know what's going to happen in the future, right? If the red circle would be identical to the blue circle, then we know that everything is going to be fine. We'll never make mistakes. Not the case. We have these blue shape regions here that reflect the disagreement, and the question is, how large are they? Okay, so the first question I want you to think about, given that we are simply talking about conjunctions now, to develop an intuition in the context of a very simple function, is the picture that I drew here correct? So remember, the true function, not yet. The true function was x2, x3, x4, x5, x100. This is f. The function we learn is this h. And I want to know whether this picture is the right one for this case. And if it is, why? If it's not, why not? And that's the question that I'm asking now. Think a little bit about it. And let's see what we have. So many of you are still thinking. So try to give an answer in a form of yes, no, and a reason. Why do you think this is a good picture? Why do you think this is not the right picture? Okay, let's see. What do you think? Okay, so as you're still thinking about it, what do I mean about the right picture or not? So what this picture shows is that H and F, or H can differ from F in two ways. This part here shows examples that are positive for F and negative for H. And this picture here shows examples that are positive for H. They're inside the red circle, but are outside the blue circle. So they are positive for H and negative for F. So my question is this the right picture? Or equivalently, in this example, do we really have these two moons, both H that is out inside H and outside F, and both inside F and outside H? And most of you say yes or no, but no reasons. So the function is linear, but I don't think that matters. But someone suggests here H should be inside F, since F contains all the positive examples in H. Okay, that's an interesting hypothesis here. H should encompass more of F than it does. And these two questions are the direction in which you should think. But you should also think about the fact that it has nothing to do with being linear or not. And again, think about this and convince yourself. Okay, so some of you, I think, have the right intuition. Let's continue and see how do I think the picture should look like. I think the real picture is this, which means H must be inside F. What does that mean? It means that in this specific case of monotone conjunctions, all the positive examples of H, this function here, are also positive examples of F. Okay? So we don't have negative examples of F that are not negative example of H. So these are two equivalent ways to say the same thing. So a third way to say it, the only mistakes we're going to make are in this moon here. Positive examples of F that are negative for H. Can someone give me an example of a point in this part of the Venn diagram? A positive example of F that is outside H.
When x2, x3, x4, x5, and x100 are 1, but x1 is 0, then H will be 0, but F would be 1.
Exactly. So let me just repeat this. Oh, what happened? sorry. Let's look at H here. If I have an example where X2, X3, X4, X5, and X100 are on, it already makes it a positive example of F. I don't care about the rest. But X1 is 0. Then it's still a positive example of F, so it's inside F, but it's negative for H because of X1. And these are examples. There are many examples like this because I don't care about the other variables. But these are examples in this blue region here, in this moon. And there are no examples that are positive for H and negative for F. Okay, so now I want to do some analysis. Basically, I want to tell you how large is this region, or what is the probability that we're going to have examples here. This really is going to define how well we're going to do in the future. The area of this region. Now notice that I plot it as if this is a flat thing, and you can think about the area of this, but really there is a distribution that goes into this into the screen above it. And some of these points weigh more than others, right? So there is a distribution, it's not necessarily uniform. So let's do some simple analysis to try to get an idea of what is this error, right? This is the error that H is going to make. And my claim is the following, or the first part of is the claim is this. Let's assume the Z is one of the literals, a variable, and I'm denoting by P of Z the probability that when I sample an example, the example is positive and Z is false in it. Right? So as in the example that I just mentioned, you know, the case where I have a positive example, so X2, X3, X4, X5, X100 are on. I don't know about the others, but I know that X1 is false in it. This is an example of the statement here, right, where Z is X1. I'm claiming that if I denoted P of Z this way, then the error of my hypothesis is bounded by the sum of all P of Z, where Z ranges on all the elements in H. In this case, over 6 elements. Why is that the case? So during learning, PZ, which I define as the probability that in a given example, when I sample an example, the example is positive, but Z is false in it, I'm just repeating it here in a slightly different way. PZ is the probability that a randomly chosen example is positive and Z is deleted from it, from the hypothesis, right? Because that's how we learn. We learn by elimination. Notice also that if Z is in F, in the target concept, then P of Z is 0, right? Because it can never be that a true literal is false in a positive example. We're learning a monotone conjunction here. So if Z is in the target concept, P of Z is 0. Note also, and this is the key observation, that H will therefore make mistakes only on positive examples. If you give me a negative example of F, it will mean that one of these guys, X2, 3, 4, 5, 100, is off, and therefore H will also make a mistake. Right? So H will only make mistakes on positive examples. I'm explaining it here. Mistake is made only if a literal Z that is in H but not in F is false in a positive example. Okay? That explanation eliminates the other moon that I had before there. And therefore, another way to think about P of Z P of Z is really the probability that Z causes H to make a mistake on a randomly drawn example, right? So I'm making a mistake if and only if I have this Z that is false in a positive example. Now, I don't know how many Z's like this exist, and it's possible that they occur together, right? So let's assume that I'm just beginning to learn now, and there are many Z's like this that should be eliminated. Maybe I get several of them at the same time. So there may be overlapping reasons for mistakes. But clearly, if I sum all the P of Z's, it bounds the error. And therefore, the error that I'm going to see is the sum of all the P of Z's over all the Z's that are currently in my H. Okay, so that's step one. Step two of the analysis. I'm going to call a literal bad if its P of Z is greater than epsilon over n. So epsilon is some error tolerance that we have. You're going to tell me, you know what? I'm willing to suffer epsilon equal 10%, 0.1. As a function of this, I'm going to name the literals, where n is the number of variables that we have. Okay, so a bad literal is a literal that is not in the target concept. How do I know this? Because we know that if something is in the target concept, P of Z is 0. We just said it in the previous slide. So if it's positive and greater than epsilon of n, then I know that a bad literal is not in the target concept. And it has significant probability to be false in a positive example. Significant, I mean greater than epsilon over n. Now, my claim is that if I have no bad literals, my error is going to be less than epsilon. And the reason is the previous claim that we showed that the error is less than the sum of all P of Z's for all Z's in H. Each one of these is epsilon over n. They are less than n attribute literals in H, and therefore the sum over all Z's in H is greater than epsilon. So basically, what we showed here is that everything now is going to be a function of these bad literals. Do we have bad literals or not? Now, what if there are bad literals? So if there are no bad literals, I'm going to be okay. I'm not going to make more than epsilon error. What if there are bad literals? Let's bound the probability that there are bad literals. So notice, bad literals are those that I'm eliminating during learning, but some of them remained. I did not eliminate. This is the X1, right? That I was not able to eliminate while learning. So let's assume that Z is such a bad literal. What is the probability that it will not be eliminated? What is the probability that it will not be eliminated by one given example? Now, the probability P of Z is greater than epsilon over n, which means that the probability that it was not eliminated, that it survived an example, is 1 minus the probability that it was eliminated, which is 1 minus P of Z, right? Because P of Z, again, is the probability that I saw Z in a positive example and it was 0, which means I eliminated it. So the probability that a bad literal like Z survived an example is 1 minus epsilon over n. I'm going to show many examples. And so what is the probability that this Z, this bad Z, was not eliminated in all of them? It's basically 1 minus epsilon to the n to the power of m. I tried it once, didn't eliminate. I tried it again, didn't eliminate it. Every experiment like this it was not eliminated with a probability 1 minus P of Z or 1 minus epsilon over N, but these are independent examples. So the probability is 1 minus epsilon to the N to the power M. It's exactly the same thing as you're asking, you have a coin and the probability of getting a head is a quarter. What is the probability that you're going to get or you're not going to get a head in several consecutive tosses of the coin, right? So it's the probability to the power M. Now, so this is the probability that P survived M in that Z survived M independent examples. Now, this is true for this Z, one of them, but there are multiple potential Z's, at most N. So the probability that some bad literal survives M examples is this probability times N. And that's it. Question so far? No question. Okay, last step of the analysis. So we know what is the probability that some bad literal survives all our learning process and stays in H even though it does not belong there. Now we want to bound this probability. We want this probability to be small. Let's assume that I want to choose M large enough. Now notice that this probability goes down exponentially fast with M. The more I add examples, the less likely is that Z will survive, right? Because this is a small number. Let's say it's 3/4. As I multiply it by itself many, many more times, more examples, this goes down exponentially fast. So, and I want to choose M to be large enough so that this is small. How small? Let's assume that I'm willing to tolerate delta. So I want to choose M large enough such that the probability that some Z survives M example is less than delta. Okay? So that's what I want. I want that the probability that Z survives, some Z survives M examples, which I showed is less than delta. And now I want to just isolate M from this inequality and tell you what should M be so that with probability at least 1 minus delta, I will make error that is less than epsilon. How do I isolate M from here? I'm going to use some inequality that many of you have seen. If you haven't, believe me, it's relatively easy to develop this inequality yourself if you remember Taylor expansions of the function e to the minus x. It starts with 1 minus x, and then there's a few other terms that are positive, and therefore e to the minus x is always greater than 1 minus x. So because of that, n is here. This is 1 minus x. Think about this as 1 minus x. So I'm going to replace this 1 minus x, but something bigger than it, which is e to the minus epsilon over n times m. So it's sufficient for me to require that this is less than delta. And now it's easier to isolate m from here. I can take log on both sides, or log base e on both sides, and do some algebra and get this. I'm not going to show the algebra now, but you should be able to take ln on both sides and isolate m from here. What you will get that m has to be greater than this expression. So if I take these many examples, I guarantee that the probability of error that I'm going to have is that the probability of failure, that is, my error is going to be greater than epsilon, is less than delta. So what is this probability? Let's look at it. It says, what is this m? What is the condition of m? M is going to go up as the error goes up, right? So if you want a very, very large, if you want a small epsilon, you need larger m. If you want small delta, you also need larger m. If you have many variables, n, you also need larger m. So all these dependencies hopefully make sense, right? So if you want to have this guarantee with high confidence, which means small delta, you need to take more examples. If you want small errors, you need to take more examples. If you have many variables, many more candidates for z's to remain in the hypothesis, you need to have larger m. So that's what we've shown. And I'm going to say it in two ways. If m is as above, then with probability at least 1 minus delta, there are no bad literals. Or equivalently, if m is as above, then with this probability, at least 1 minus delta, my error is going to be less than epsilon. So this blue moon that we showed is going to have a small distribution over it, distribution that is smaller than epsilon. Okay, questions?
So there's two questions in the chat right now.
Yeah, okay, so let's attend to the question how do literals get removed from H? So if we go back to the way we thought about the algorithm for learning conjunction, we get an example. We get a positive example. X7 is 0 in this positive example. What does that mean on X7? It means that it cannot be part of the function. So we eliminate it. And now H does not have X7 in it. That's
Okay,
how
so
we eliminate variables.
Okay, yeah, so it just translates to setting one of the features in the sample to 0, which would eliminate it from the conjunction.
Not setting. I'm not setting anything. Someone gives me examples. And then they label the examples. The example is a vector of 100 bits, zeros and ones. I'm trying to learn the hidden conjunction. My initial hypothesis is that all the variables are in the conjunction. So my initial hypothesis is x1, n x2, n x3, n x4, up to x100. I'm repeating a process that we've done a couple of weeks ago when we learned this conjunction. Now I see an example. The example is a positive example, and x7 is 0 in it. Okay, the seventh coordinate in this 100-dimensional vector is 0 in it. That tells me that x7 cannot be in the true conjunction, right? And therefore I eliminated it from H. So my H now is x1 and x2 and x3 and x4 and x5 and x6.
Sure.
And x8 and x9 and so on.
Sure.
That's how I eliminate it. And this was the basis of all the analysis that I did, that I denoted by P of Z, the probability that a literal or a variable will be eliminated from the hypothesis, which means it's a positive example and Z is 0 in it. And now with this in mind, go back to the 3 steps that we described. Step 1, where we define what P of Z is, and convince yourself that you agree with this claim. Okay.
So P of Z being the probability that a sample or a literal won't survive. I guess I'm still not following. I get that. I get the samples. I get conjunctions. I'm trying to get to the derivation of PZ.
PZ is defined this way. The probability that the example is positive and Z is false in it. So I'm drawing an example. I have a huge number of examples to draw for. I got a positive example. There is some probability that X7 is 0 in it, and some probability that X7 is 1 in it. PZ is the probability that a given literal, let's say X7, is false in a positive example. And I also told you here that if Z is actually in F, in the target concept, then the probability of PZ is 0, because it will never be false in a positive example. But for other variables, it will be positive.
And this is based off of the labels where, like, comparing how many examples where it's positive and the label's positive versus where it's negative.
No. So there is a space of many possible examples. Some of them are positive, some of them are negative. Among the positive examples, some of them have X1, 0. Some of them have X7, 0. Some of them have X7, 1. Some of them have X19, 1. Some of them have X21, 0, and so on. The distribution is over the space of the examples.
Yeah, I think that's what I was asking. I think we were saying the same thing. It's over all the examples where
Right.
a given literal is either positive or negative, and then taking the probability.
Yes. And I don't know this distribution. I don't know what is the distribution, but I can reason about it. And I'm reasoning about it this way.
So is that contingent on the size of the number of examples that there are?
No, it's a distribution over all the examples. I'm just sampling from this distribution and observing examples.
Okay.
The number of examples are the Boolean examples over 100 variables is 2 to the 100. I'll never see all of them. But there is some distribution over them. Maybe some of them are very frequent, and some of them have 0 probability on them, and I'll never see them. I don't know what is this distribution.
Okay.
But I can reason on this, and the reason I want to reason of this is because I want to get an estimate for how many examples are in this region here. This blue moon that I show, that is inside F but outside H. And what these 3 slides have shown is that I can reason about this, and I can show that if I want to make sure that the probability of this region is less than epsilon, there is a certain number of examples I need to take, because as I take more examples, H grows and become closer and closer to F, right?
Okay,
That's the process that we have.
Mhm.
How many examples do I need to take until this blue region, remaining error, is less than epsilon? That's the question I want to ask.
Understood.
Okay?
Okay, it's making sense now. Thank you.
So now, I will not go over all the details here, but with this in mind, go over the details, and you will see that what we showed is that we want to grow this h until it approximates f well enough. What does it mean, well enough? Well enough, it means error less than epsilon. This area of this blue moon is less than epsilon. Now, we cannot be certain that it's going to be less than epsilon because this is the probability that it will be less than epsilon. This is the probability that some bad literals survive M examples. So I cannot be certain, but I can say, you know, okay, if this is the probability, let's make sure that this probability is less than delta. And when you agree on this delta, I can tell you, oh, okay, if you agree on this delta, then make M be this. Make M be greater than this expression here, and you're sure that the area of the moon is going to be less than epsilon. That's the analysis that we've shown. Now you can plug in some numbers here. Delta 0.1 and epsilon 0.1 and n is 100. You need almost 7,000 examples to make sure that with probability at least 90%, the error that you will make is less than 10%. If you take, I don't know what's happening here. The next example was where n is only 10. Again, delta and epsilon are 0.1, n is 10. You only need 460 examples in order to guarantee that with probability 90%, the error that your hypothesis is going to make, that is the area of this blue moon, is less than 10%, and so on. So basically what we did is we gave a guarantee that our algorithm is going to be pretty good, 10% error, a probabilistic guarantee. More questions on this? Okay, so let's just step one level up and see what we've done here. We've formulated a prediction theory. Our instance space is X. We make prediction with hypothesis from X to Y on some unknown distribution. That's the key here. We don't know what is the distribution. S is the set of examples that we've seen. It was drawn from this distribution over X cross Y. And with this notation, we can define the true error. The true error is the probability over the distribution over X cross Y that H is different than Y. We also define the empirical error, the error on the training data, which is the probability over X cross Y in S that H is different than Y. Or you can just think about it as the number of errors we're going to make. Now, given that we have these two concepts, we can ask, can we describe or can we bound the true distribution when we are given the observed, the true error, given that we have the observed error? We always have the observed error, right? So you train your algorithm, you know what the error is on the training data. We care about, can we use this to describe or bound the true error, because that's what we care about. And that's what we did one step toward now. That's question one. There's another question we want to ask. If you tell me, oh, you know what? I have some set of true functions, the target functions that I'm after, and I'm using my hypothesis space H to learn it. The second question is, can I even learn functions in this space? Do I have any chance of learning this? And in order to do this, I have to come up with a more rigorous definition of what does it mean that I can learn it, of course, it will have something to do with my true error, right? Because if I cannot limit the true error, I haven't learned anything. But it will have a few other components to defining learnability. The question is it possible to learn a given function C using functions in H given my supervised learning protocol? And hopefully the intuition that we developed so far says, really, we cannot expect to learn a concept exactly or a hidden function exactly, because first of all, given that I gave you some training data, in general, there are going to be many concepts that are consistent with this training data, right? Because the training is always a small fraction of the set of all possible examples in the instance space. So unseen examples potentially could take any label. Well, not exactly, because it's not general functions. I'm just talking about functions in some specific class of functions. But still, there could be many functions consistent with my training data. So therefore, I'm willing to agree to misclassify some examples. Hopefully, I'm going to misclassify some uncommon examples that did not appear in my training set. Now, moreover, I cannot always expect to learn a close approximation. I cannot always expect that this H is going to be very close to F, because sometimes maybe the sample that you gave me, my training set, wasn't a typical one. It wasn't a representative training set. It did contain some uncommon examples, and I learned using these, and therefore my approximation isn't a close approximation. So these are two issues that are distinct issues. And together, the only realistic expectation that I can have for a good learner is that with high probability, I will learn a close approximation to the target concept. Again, the close approximation means that this H is pretty close to F. This blue moon is small. That's the close approximation. That's my epsilon. That's the error that H has. And I want this to happen with high probability. And the high probability is going to be over the training set that I've seen. If I was so lucky to get a pretty typical training set, it's going to happen with high probability. If I was unlucky and the training set wasn't a typical one, I will learn something, but it's not going to be a close approximation. And of course, the larger the training set is, this probability is going to be higher. And these two key concepts lead me to a definition. Question so far on these two components. So hopefully this is very intuitive, and hopefully this simple example of H and F that we played with so far brings this home. And now I can make a definition, which is really a key definition that was made in 1984, which is a long time ago now, by Les Valiant, where he defined learnability. And actually, it was the first time that people gave a rigorous mathematical definition for what does it mean to learn. And really, everything is driven by this that I'm going to repeat. We cannot expect a learner to learn exactly. And we cannot always expect to learn even a close approximation, because the training data might have been atypical. And therefore, the only realistic expectation is that with high probability, we will learn a close approximation. So the probably approximately correct learning requires that, given small parameters, epsilon delta, you come up with the epsilon delta that you're willing to tolerate. With probability at least 1 minus delta, a learner produces a hypothesis with error at most epsilon. And we're going to attend to the next sentence a little bit later, but that's the picture that you want to have in mind, right? So you have some hidden F, the blue one, in mind, and you're going to see examples and learn H. And what you want is you want to narrow or reduce the size of these symmetric differences here, right? F that is outside H and H that is outside F. The differences between H and F. We consider a concept class F, C, sorry, that is defined over an instance space X with instances of length n. We have a learner L that makes use of the hypothesis space capital H. And we're going to say that this set of functions is learnable using algorithm L and hypothesis H if for all functions, for all hidden functions in C, for all distributions, and for some fixed epsilon and delta, the algorithm L, given a collection of M examples that are sampled independently according to D, produces with high probability, at least 1 minus delta, a hypothesis that has at most error epsilon. And we want this to be done where the number of examples is polynomial. Computer science, it's all about polynomial scaling, and M must be polynomial in 1 over epsilon, the error parameter, 1 over delta, the confidence parameter, N, which is the size of our instances, and the size of the hypothesis space. That's the definition of learnability. We are also going to say that it's efficiently learnable if L is an efficient algorithm. That is, L can produce this hypothesis in time that is polynomial to the same complexity parameters. Okay, so let me just summarize what we've said so far. We really imposed 2 limitations. We said something about the sample complexity. This is a condition of how many examples do we need to see so that we are sure that the hypothesis we've learned is good enough. Basically, we're asking, is there enough information in the sample that we've learned to distinguish a hypothesis H that approximates F well enough? We also talked about, and this is kind of the secondary condition, is how efficient is L? How efficient is the algorithm that allows us to compute H? And notice that to be PEC learnable, there must be a hypothesis with arbitrary small error for every function in the target class, right? Because you choose epsilon, you can choose epsilon to be very, very small. Now, we typically assume that the set of hypotheses H is a superset of the set of target functions. If it's not the case, then we cannot even express the target function. So we will never have training error 0, for example. Of course, in real life, we're going to relax this. But for now, when we have a definition, a theoretical definition, we can assume this. Notice also that this is a worst case definition. The algorithm must meet its accuracy for every distribution. This is called sometimes the distribution-free assumption, and for every target function in the class C. And this assumption turns out, the first one turns out to be a very important assumption. We're going to address it a little bit later. The second one doesn't really matter because everything relies on H, it turns out. And it doesn't matter where the target functions are coming from. Okay, So I want to summarize and stop here. Really, we are looking for a theory so that we can understand what does the observed performance on the training set says about future performance. And we want to be able to understand what contributes to this gap between what we see on training and what we see in real life. And this theory of learnability is going to allow us, as we've shown before, when I started this lecture today, to understand this complexity gap. What determines the gap between what you see on training and what you see on test? So next time we're going to continue with this and say a little bit more about how to what are the complexity parameters that contribute to this gap, and basically generalize the simple example that we've shown with conjunctions, where H grows into F, but leaves a sliver of a moon there, and we want to quantify the size of this blue moon. Questions? Okay, there's a question here on the difference between the concept class and the hypothesis space. So the key concept is that of hypothesis space, which is the collection of functions that your learning algorithm is allowed to use. If you learn decision trees, then H is the set of the decision trees. If you limit the size of decision trees, then your hypothesis space is decision trees of depth 4, for example. If you're learning with perceptron, your hypothesis space is the set of all linear functions of some dimensionality, and so on. Now, the concept class is just an imaginary notion, the set of all functions where the hidden function might be. Maybe there isn't even a set like this, right? Because really what you're learning is something very noisy. It's not consistent with any function. But we can always imagine that there is a hidden function, and this hidden function is taken from a collection of functions that we call C, because it helps us think about how good H is. Right? So if you imagine that all your functions are linear functions, then choosing H as a set of linear function is good enough. If you imagine that really the target function is a lot more expressive than linear functions, then maybe H being a linear set of linear function isn't sufficient. So C you can think about as a set of target functions, or as something in your imagination, in your understanding of the domain, that tells you the target functions are probably like this. Is today's class included in the exam? There was a question at the beginning on that, and I said that conceptually, yes. I will not ask you to reproduce the proof that we did, but I do expect that you understand the conceptual perspective that we expressed today. Now, between today and the exam, there's going to be many office hours of myself and the TAs. There's going to be a recitation tomorrow. Please use it to ask questions that you have. Go back to the first slide where I talked about what the exam is like. And other than that, I'm going to see you at 10:30 on Wednesday. Be there a few minutes before 10:30, so you'll be ready to start at 10:30. And as I said, be on Zoom so we can communicate, and if at all possible, open your video, and that's it. Any final question?
Sorry, yeah, I have one. So when in the beginning we were talking on the learning conjunctions analysis slide, like the first one, where we made the claim that H only makes mistakes on positive examples. So that diagram's different than the one on the probability of the probably approximately correct slide. And I guess I was just trying to determine the difference between that Venn diagram that corresponded with that claim versus what's on the I guess like the one that's like 3 slides ago. That one, yeah.
This one.
Yeah.
So that's the general case. The general case is that you can have positive example of F that are negative for H, are outside H, and positive example of H that are outside F, so they are negative for F. That's the general case.
Sure.
We gave an example of monotone conjunctions just to develop some intuition in the context of a very simple function. And in that example, I wanted you to understand that it's a special case and this is not this picture.
Okay.
Because there are no cases that are positive for H and are negative for F in that case.
Awesome. All right, that makes sense. And then one last thing is the epsilon in this case would be everything that's not overlapping, right? So you have the Venn diagram, you have the overlapping positives, and then epsilon would be both sides of that.
Exactly. Epsilon is this error region. In this case, it's this moon here and this moon here together constitute epsilon.
Understood. Thank you.
Any other question? Again, their office hours, mine is today at 5. Many TAs have today and tomorrow office hours. Please use it. And other than that, I'll see you on Wednesday. Bye.
Thank you. Bye.